Good morning, myself Vidya. I'm here to present the paper Design and Development of an Animatronic Hand with Adaptive Graphics. My co-authors are Binu LS and Vivek Dia. I'm from Department of Electronics and Communication, College of Engineering, Trivandrum. So outlines include introduction, motivation, literature review, objective, methodology, block diagram, testing and evaluation, results, future scope, conclusion and references. So the paper focused on design and development of a compact human mimicking animatronic hand that can perform adaptive grasping of various objects. So proposed robotic hand is used with the six degree of freedom and actuated mechanism. By integrating advanced control algorithms, tactile feedback and precise actuation, this project seeks to create a responsive robotic hand suitable for diverse applications in the field like assistive technology, automation, and human-robot interaction. So the main motivation behind this project is robots have excelled in structured manufacturing environment, but faces challenges in unstructured environment like household tasks. So the inspired by the human hand, which is a remarkable biological tool capable of executing everything, we have proposed this hand. So I have gone through many of the literature surveys, and so the literature covers a wide range of work in the field of robotic hands. High-end systems like shadow hand and DLR hand, which are markedly available, are costlier, complex, and bulky, while affordable options like InMove lack real-time adaptability and precision for handling delicate objects. So the main gap remain in the area is reduced force transmission efficiency, wear out, and durability over time due to the repeated high load cycles. So these are the two type of finger and effectors. Less than three finger means gripper type, and greater than three finger means anthropomorphic type. We are using anthropomorphic type here. So objective is to design human mimicking animatronic hands with five finger capable of adaptive tasking and to integrate actuator for precise movement control and to develop a control algorithm for force and position control and to incorporate tactile sensor on the fingertips to detect slip and adjust the grip dynamically and to ensure a hand can grasp a sponge ball with stability and reliability. So methodology include understanding the existing technology and identify the gaps, create detailed 3D model using Fusion 360, utilize actuators and prototyping, ensure smooth integration of sensors and actuators, then conduct rigorous testing to validate the performance. So this is the system block diagram. Here we have robotic hand prototype which has a pressure sensor attached at the fingertip and a visual sensor placed static. An Arduino Nano control board and Raspberry Pi control board are used as the control boards and servo motors are used connected to the Arduino Nano. Here, the servo motor is powered by using DC power supply. So this is the robotic hand design consideration. Here, approximate weight of the hand should be 500 grams. Size of the hand is similar to the human hand size, and the hand configuration is 5 fingers, 6 motor, 11 joints. Degree of freedom is 6, and operating voltage is 12 volts. The fingertip force is 3 Newton, and the maximum force lifted should be up to 30 Newton. So this is the single finger link and joint design. I have designed, and you can see DIP joint, PIP joint, and MCP joint. These are connected by using the link 1 and link 2 we have designed. So the linkage system connects the joints to distribute grasping force based on the object shape. A tendon-driven mechanism controls finger movement, allowing individual flexion and extension. Each finger is actuated through tendons using single motor per finger for efficient control. So these are the mechanical calculations done for design. So the robotic hand we are using is for spherical ball objects, and the force required for grasping the ball is F equal to mg. That is total force needed to hold the ball against the gravity is 0.0981 Newton. And we have find out the fingertip force by dividing it with 5 as each finger shares load equally. And also frictional force is also find out by frictional coefficient for the sponge ball, that is mu equal to 0.6. Torque is calculated by fingertip force into total finger length. So we have calculated torque for each fingers and all torques are within the MC90 servo limit. So proposed hand mechanical setup. Proposed hand was designed and 3D modeled using Fusion 360, fabricated and assembled as you can see in the figure. And the system is 3D printed using PLA and later add silicon cover for skin texture. Here we use MC90 servo motors to drive finger tendons, which are placed at the palm for compact design. And FSR sensors are 5 in number placed at the fingertip for real-time contact pressure sensing and avoid deformation. And webcam module is used for visual servoing. The control system includes microcontroller and Raspberry Pi housed at the base for efficient hardware-software communication. Initially, position control move the finger and monitor by using a buck converter and Raspberry. It is given to Raspberry Pi Model B. And here, a serial communication is happening between Raspberry Pi and the Arduino Nano, and a USB camera is connected to Raspberry Pi, and prototype FSR sensors and the NG98 servos are connected to the Arduino Nano. So this is the control system flow chart. You can see here I am using SpongeBob as the object. So here roast to node is initiated and the camera is initiated. It starts with the camera feed and camera takes the frames and apply algorithm for object or ball detection and shape detection algorithm. So detect the ball or object and hand pose estimation and MCP coordinates. Hand pose estimation is done by using media pipe and we need to find out after once the object is detected, its position coordinate should be computed. So that is the position coordinates are x1, y1 and x2, y2. We have to come by using we have to find out the coordinates that is MCP coordinate is x2, y2 and after finding the coordinates we have to keep a distance threshold also. After that, a based on the trigger assigned, that is hand position is it should be out of palm and the system should apply actuation then if the hand position is triggered. So we will check for aligning and triggering. If trigger is out of palm, it should be yes, and it manually move the hand towards the object and it check for the distance threshold. If the distance threshold is achieved yes, it start actuation and it grabs the object. We after that we have if FSR sensor come in contact with the object, there should be a threshold for the tactile force also. If this threshold is also achieved, it will stop servos without deforming the object. If no, it will actuate and check for whether the object is getting deformed or not. So this is the test setup. A sponge ball is placed on flat surface and the robotic hand is commanded to grasp it and manually and physically. Manipulate it physically and the camera is placed upside down to cover the work area. 5 volts of power supply is given. Controllers are connected to the circuit. So testing and evaluation is done by finger strength estimation test during FSR sensor is done. Using the FSR sensor is done. That is from this we need to increase the force per the finger. So the average grip force should be greater than 0.5 Newton. After that, I have created a deformation model by collecting the data by increasing the grip force on the sponge board. And from this result, deformation increases linearly up to a force of 3.5 Newton. And after that, it saturates. So we get a deformation model. So results include design the linkages of the finger and developed the hardware model of the 5-finger robotic hand, tested the prototype in real time by integrating sensors and actuators and control algorithms. So the experiments were conducted on the object sponge ball and it successfully grasped. This is the video showing the controlling of animatronic hands. This is the hardware setup as you can, as I have shown you already. This is the servo testing. This is the sensor testing. I am taking the values of the sensor here. So this is the console view of vision-based robotic hand testing. So testing done in different conditions is given. Hold, grasp and release to try to grasp and release. After that, I have added the skin and it grasped properly. So this is the RQT graph which visualize the changing nodes, topics and connection between them. The graph validates the robotic and algorithm how it effectively detected and grasped the object. So this is the console view of the sensor value and when the object is grasped. The graph shows the exponential curve for each finger, that is the nonlinear relationship between the force and the resistance, where resistance increases when force decreases. So this graph is the performance graph showcasing the force that is RBO hand is more similar to the proposed hand. It has less gripping force and deformation saturate. So proposed hand achieves 27.5 deformation with only 3.5 Newton, showing high efficiency. It offers a good balance of low weight. RBO hand is also achieving maximum deformation suitable for soft grasping. In conclusion, the proposed hand is optimal for soft robotic applications. So this project showcases the design and development of a robotic integrated animatronic hand capable of object detection and adaptive grasping and real-time control. By combining vision, force feedback, and untracted mechanisms, the system delivers reliable, stable performance. Thus, the project aims to push the boundaries of animatronic hand design by integrating advanced control techniques and tactile feedback. This successful completion of this project will contribute to the field of robotics and prosthetics. So, future scope includes key area of improvement is PID tuning of servo motor can be done. AI-based optimized graph strategies should be done by integrating control algorithms, adding tactile and vibration sensors using stereo and depth camera for improved object detection. These improvements will facilitate application in medical procedures, industrial automation, etc. So that's all about this. These are the references I have referred, and thank you.